In 1955, an Air Force engineer named Clark Beck created a new material for NASA that would permanently alter the future of space travel. What he designed was a reflective foil film capable of bouncing back 95% of radiant heat. The concept sounded simple. The impact was enormous. Without that breakthrough, modern space missions would never have functioned the way they did. The material became part of spacesuits, lunar landing vehicles, the space station, and even the James Webb Telescope. After the technology later moved into the public domain, it found an entirely different purpose on Earth. It became one of the most effective ways to limit unwanted heat entering residential buildings. Today, people know it as a radiant barrier. The material can cost as little as 10 cents per square foot. Even so, studies showed it could lower attic temperatures by 30 degrees Fahrenheit while reducing household cooling expenses by as much as 17%. Yet despite being among the least expensive and simplest upgrades for reducing summer heat gain, estimates suggest fewer than 10% of existing homes across the United States currently use radiant barriers. This video explains what radiant barriers are, how they operate, and why a homeowner can potentially cut hundreds from a summer cooling bill after only a few hours of installation work. Before understanding the barrier itself, it is necessary to understand how heat enters a house in the first place. Heat moves in three separate ways. The first is conduction. This happens when heat travels through solid materials through direct contact. As the exterior shell of a house becomes hotter, that energy slowly transfers inward into the living space. Depending on the insulation level and the materials used in construction, conduction typically accounts for roughly 10 to 30% of a home's heat movement. The second process is convection. This is heat carried by moving air through drafts and circulation currents. Warm air can enter through openings around rim joints, gaps near windows, or spaces around doors. Like conduction, the impact changes from one structure to another. In most homes, convection is responsible for approximately 15 to 30% of heat gain or loss. In older and draftier houses, that figure can approach 40%. Then comes radiation, the largest source of unwanted heat gain. Radiant heat moves through electromagnetic waves, similar to the warmth felt from sunlight against skin. This process can represent anywhere from 40 to more than 65% of the total heat entering a building. Windows are an obvious source because sunlight carries both visible light and heat energy. But outside of windows, the attic remains the single largest contributor to unwanted summer heat. Imagine a hot afternoon in July. Sunlight strikes a dark asphalt roof and the surface absorbs massive amounts of energy. The underside of the roof deck effectively turns into a giant suspended radiator hanging above the ceiling. That creates multiple problems at once. If HVAC ductwork passes through the attic, research has shown the added heat can increase system load by 22%. That raises electricity costs, while also placing additional stress on the cooling equipment. As the roof continues radiating heat downward, another effect begins. Air itself absorbs very little radiant energy. Because of that, much of the heat travels across the attic space until it reaches a solid surface, most commonly the insulation resting on the attic floor. The insulation absorbs that energy, becomes warmer, and gradually transfers the heat into the rooms below through conduction. Architects and engineers recognized this issue decades ago, and early forms of radiant barriers have existed since at least the beginning of the 20th century. The earliest reflective foils designed for buildings received patents in Germany and the United States during the 1920s and 1930s. By the 1940s and 1950s, companies including Infra Insulation were already marketing foil insulation products directly to homeowners across America. The early products attracted some attention, but widespread acceptance never happened. Most homeowners simply did not understand how radiant heat functioned, so the technology failed to spread into the mainstream market. That began to change during the middle of the 1950s. As the space race started tightening its grip on the United States, a young United States Air Force engineer named Clark Beck received an assignment involving a dangerous problem. A spacecraft was at risk of ripping itself apart during atmospheric re-entry as it skimmed across the upper atmosphere. He referred to the issue as red-hot wings. That challenge pushed him deeper into radiant barrier research. Eventually, NASA developed a manufacturing method that sprayed an ultra-thin layer of vaporized aluminum onto plastic film. The result felt similar to cellophane, yet behaved like polished metal. It reflected more than 95% of incoming radiant heat while weighing only 17 pounds for every 1,000 square feet. The material quickly solved multiple aerospace problems. Beyond Earth's atmosphere, air does not exist. In that environment, radiant transfer becomes the only natural method of heat movement. Temperature swings there are extreme. A spacecraft or astronaut suit can move from temperatures above 500 degrees under direct sunlight to more than 400 degrees below zero in darkness within seconds. Using traditional insulation to shield astronauts from those conditions would require a suit nearly 7 feet thick to provide the same level of protection. For a period of time, the reflective film remained limited to aerospace applications. Later, it entered the public domain. Then the oil crisis of '73 drove energy prices sharply upward, and the material rapidly appeared in residential construction as a low-cost energy-saving solution. The reason such a thin foil layer can either protect astronauts in space or lower attic temperatures by as much as 30 degrees Fahrenheit comes from two connected physical properties: reflectivity and emissivity. Reflectivity describes how effectively a surface sends radiant heat away from itself. Emissivity works in the opposite direction. It measures how efficiently a material releases radiant energy after absorbing it. For solid materials, those two values always combine to equal 1. A black asphalt roof shingle, for example, reflects only around 10% of radiant heat, while re-radiating the remaining 90%. Clean aluminum foil behaves almost completely opposite. It reflects roughly 95 to 97% and absorbs only 3 to 5%. But every radiant barrier also faces an important engineering limitation. The reflective surface must sit next to an airspace. Radiant heat transfer can only be disrupted when the reflective material faces either a vacuum or a gas, which in residential construction means air. If foil becomes trapped directly between two solid surfaces, such as plywood or gypsum board, heat bypasses the reflective effect through conduction. Because of this, at least one side of a radiant barrier must face open attic air or maintain a minimum 1-inch air gap. Once the underlying physics become clear, the concept behind radiant barriers is surprisingly straightforward. Even so, the effect can be substantial. Oak Ridge National Laboratory tested several radiant barrier systems inside a climate simulation chamber operating at 140 degrees. Their findings showed that foil stapled beneath rafters reduced heat flow by nearly 50%. Foil installed across the attic floor lowered it by roughly 1/3. A liquid reflective coating sprayed onto the floor reduced heat movement by 19%. Outside laboratory conditions, the performance continued showing measurable results. A monitored study involving 8 upgraded homes in Central Florida found that radiant barriers reduced cooling energy consumption by an average of 9%. The same study also lowered peak cooling load, the period that places the greatest stress on an air conditioning system, by approximately 16%. For a house measuring between 1,000 and 2,000 square feet, the monthly reduction in cooling costs worked out to around $13 to $27. That may not sound massive at first glance, but for a system that can be installed personally over a single weekend for only a few $100s, then continue functioning year after year, the value becomes difficult to ignore. The effectiveness of radiant barriers is already clear, but before installation begins, there are several important details to understand. The first is that performance changes depending on the type of home and the surrounding climate. In regions with long, hot summers, radiant barriers perform extremely well. In colder environments, however, the reflective surface also pushes away useful winter solar heat that might otherwise help warm the building. Another key point is that attic radiant barriers are far better at rejecting heat from entering a house than trapping warmth inside it. The reason is simple. During winter, most household heat escapes through convection rather than radiant transfer. Still, there is one location in cold climate homes where a radiant barrier remains highly effective. Not in the attic, but beneath the floor. Modeling studies found that this application can reduce total floor heat loss by nearly 95%. Long-term performance also matters. Radiant barriers require very little maintenance, but dust creates a major problem. When foil is laid flat across attic insulation, household dust gradually settles on the surface. Over time, the bright reflective layer turns dull gray and begins absorbing heat instead of reflecting it. One study discovered that reflectivity could decline by a factor of 10 within only 2 years. In many cases, the dust responsible was not even visible. This is one of the primary reasons some experienced installers suspend the foil vertically along the rafters instead. There are also several smaller factors worth considering. If HVAC ducts are not located inside the attic, the benefit becomes smaller because protecting duct air is one of the most important advantages provided by the barrier. And since aluminum conducts both electricity and radio waves, a continuous metallic layer can slightly weaken Wi-Fi or cellular signals passing through the roof. In most homes, this is unlikely to matter unless signal strength problems already exist. Once the operating principles are understood, installation methods become straightforward. For new construction projects or roof replacement jobs, foil face sheathing, often called Radiant Barrier OSB, is usually considered the best option. The structural panel and reflective surface are installed together in a single step with almost no additional labor required. When high-quality boards are used, they can reflect as much as 97% of solar radiation. For existing attics, the most proven retrofit technique is the staple-up method. This involves attaching reflective foil to the underside of the rafters, while maintaining the air gap necessary for proper reflective performance. Material prices usually range between 10 and 50 cents per square foot, allowing many installations to be completed for only a few $100s and a weekend of labor. For homeowners handling the work personally, perforated foil should always be used instead of solid foil that allows moisture to pass through safely rather than trapping humidity inside the attic and creating mold problems. Ventilation openings must also remain unobstructed. Soffit vents, ridge vents, and gable vents should never be blocked because doing so interferes with the building's stack ventilation system and can actually increase attic temperatures instead of lowering them. At its core, the radiant barrier is simply a thin metallized film. It was created from the challenge of keeping astronauts alive in space. Its function relies on a single principle. A reflective surface does not absorb the energy it sends away. And during summer, the largest portion of heat entering a home arrives not through touch or moving air, but through invisible radiation that conventional insulation was never designed to stop. If this information was useful, continue exploring more ideas connected to self-sufficient and off-grid living. And the next discovery may be even more surprising than a sheet of foil inside an attic, because something as simple as a PVC pipe buried beneath a backyard can produce effects most homeowners never expect. Thanks for watching. See you in the next one.